All right, welcome to the second video in this sequence of videos on orders on sets. So in this video, we're going to talk more about our examples of partial orders that we saw last time. We saw the standard orderings on numbers, and also another example of a partial order, which is sets of sets ordered by subset containment. So in this video, we're going to look at those examples, we're going to see how they're similar, how they're different, and we'll talk also about total orders. We'll define that concept, which will be important going forward. Before we begin, I just want to make a quick note on terminology. In the previous video, I was a little bit loose about my terminology. I used the terms like order and ordering and partial order all kind of interchangeably, and I think that is kind of fine to do in practice in mathematics, but for the purposes of these videos, going forward, I'm going to try to be more precise about that. So in this video and the future videos, I'm going to try to use the correct technical terms in every case. For us, that'll mean all the orders, all the notions of ordering in the previous video that we talked about. I should have been saying partial order in every case. That's the correct technical term. And that's the term we defined last video, if you remember that. So we had this definition of partial order from last time, which was a set of ordered pairs satisfying a bunch of axioms. And I didn't actually write down any really concrete examples of a partial order. I did kind of write some down, but they weren't so concrete. So in this video, I'd like to start with a really specific example. We're gonna let's let R be the partial order on, when I say the set containing 1 is going to be one of our elements, the set containing 2 is going to be another element, the set containing both 1 and 2, that's going to be another element, the set containing 1, 2, and 3, that'll be another element, and finally we'll have the set containing 1, 2, and 4. So this is going to be a partial order on a set of 5 elements, and as a result, what it means to be a partial order is that R is going to be a subset of this set cross itself. So let me call this set maybe X or something. So we're going to have R is going to be a subset of X cross X, and it has to satisfy those 3 axioms we laid out in the previous video. That is the reflexivity, the symmetry, and the transitivity. So I haven't told you what R is going to be in our example. This is going to be defined by subset containment. So this is the example we saw from last time where we can partially order any set of sets via the notion of subset containment. So I'll be precise about what that means. This is just repeating what we saw last time. R is going to be the set of ordered pairs S comma T in X cross X such that S is a subset of T. So let me just write out S subset of T. Okay. So that's going to be our partial order R. And I'd like to just take this example to write out explicitly what the set R is. What is the set of ordered pairs R? So we can see exactly how this is supposed to work in general. Here, the set of ordered pairs in R, well, we can think about it by remembering, okay, R is going to be the set of pairs S comma T, where S is a subset of T. And S has to be an element of X. That's what it means for S comma T to be an element of X cross X. So I can think about each element of X, and then think about what it could be paired with, and then make all the pairs of like that first thing, comma, possible second things. That'll be my set R. So the first thing I could have in the first slot in an ordered pair is the set that contains just 1. Well, okay. Now I ask, which other elements in X should this element be paired with? Which pairs should be in the set R? It should be the pairs where I have another set here that comes from X that contains this set containing 1 as a subset. And that's actually almost everything here. So this contains 1, this contains 1, this contains 1. This one doesn't contain 1, so that'll be missing. So let me write out those ordered pairs. This will take a little while, so maybe I'll speed this up in post. And these are all of the ordered pairs in R that will contain the set containing 1 as the first element in the ordered pair, and some other element of X as the second element of the ordered pair. So that's what I've listed out here. But of course, R is going to have more elements than this. There are going to be ordered pairs where this first thing isn't the set containing 1. Maybe we'll have pairs where the first thing is the set containing 2, right? That's another possible thing that could appear in the first slot. So let's write out those cases. Okay, those were the ones that have the set containing 2 in the first slot. And I'll continue. We'll do the next set in our set. So that's 1, 2. That could be in the first slot. And then what will come next is anything that contains the set 1, 2. So here we have these 3 possibilities. Those contain 1, 2 as a subset. So we'll get those. Okay, so that's all the elements that have 1, 2 as the first thing in the ordered pair. And what else did we have? We have 1, 2, 3 and 1, 2, 4. So we'll do those next. Okay, so that is the entire set R, written out completely explicitly. These are all of the elements of R as formally defined as the set of ordered pairs. And that's the partial order R that we care about here. In the previous video, I denoted R with the subset or equal to symbol, which is totally fine in a common convention. But we don't have to call it less than or equal to symbol if we don't want. Sometimes that's convenient, and in this case I wanted to call it R for some reason. I'm not so sure myself. Okay. So maybe that was a bit boring. If so, good. It means you understand the concept pretty well. If this was confusing, I recommend you try to check the axioms. So hopefully it should be clear that these are the pairs I described here. And it's probably a good exercise if this was strange to go and check that all the axioms we listed in the previous video actually do hold for this set of ordered pairs. This satisfies the reflexivity axiom, the symmetry axiom, and the transitivity axiom. But I claim that is true, and maybe that's obvious to you, in which case great. So now that we know exactly what R is, let's try to draw schematically what this ordered set is going to be. And I guess just quickly, an interlude. A poset, which is just short for partially ordered set, is an ordered pair x, R, where x is any set and R is a partial order on X. So this may be reminiscent of the definition of vector space, for example, where a vector space was an ordered triple of a set of vectors with a function that described the addition operation and a function that described the scalar multiplication operation. And so we have something similar here. A poset is something that has more structure than a set. It has a set of elements, X, together with this information of how those elements are ordered. That's the set of ordered pairs R. So putting those two data together, we get this idea of a poset. And we'll use that term reasonably often. It is a standard term throughout mathematics. You'll see it a good amount. Okay, so let's try to draw schematically what this poset looks like that we described up there. So this is going to be some kind of picture of that poset in some vague sense, and I'm going to draw it like this. Okay, so let me try to explain what I mean by this drawing. This is a kind of drawing you'll see pretty frequently when people try to describe posets to you. And what this is indicating, well, first of all, we see the 5 elements of our set X, right? Each of those elements of the set X appeared in that drawing as one of these objects that we see here. So those were our 5 elements that we're ordering. And the order itself was by subset containment. So the smaller sets are the ones that are, like A is smaller than B in this sense, if A is a subset of B. And that's what these lines are indicating. A line in this picture is indicating that the number that's vertically lower is less than or equal to the object that's vertically higher. So because there's this, like for example, there's this line here between 1, 2 and 1, 2, 4. This is indicating that 1, 2, so this line here indicates that the ordered pair 1, 2 / 1, 2, 4 is in the partial order R. So other ways to say this, we remember from last time, we have some shorthand notation for this. We could say 1, 2 R 1, 2, 4. That's just another way to write down that statement I said. And something you might say in words is the set 1, 2 is related to 1, 2, 4. And you might say by R. So these are all ways to say the same thing, that this ordered pair is an element of R, that 1, 2 R 1, 2, 4, or that 1, 2 is related to 1, 2, 4 by R. Okay, so that's what these edges are telling us, but these edges aren't giving us every ordered pair that appears, right? We remember that in the partial order, we did have pairs like set containing 1, set containing 1, 2, 3. Let me just look above to our listing of all the ordered pairs to make sure that was there. And yes, here it is. There's that pair of set containing 1, set containing 1, 2, 3. So one question we might have is, why in this picture did I not draw a line from here to here? The answer is I totally could have. And if I had drawn this line, it would be a perfectly valid picture of a partial order, and people would still understand what you mean. But remember that what these lines are telling us is that the lower thing is related to the higher thing, right? These are like this vertical separation between the elements is telling us that when we see a line, we can tell that this thing is supposed to be that this thing are this thing, or that this thing are this thing. And so because I have these two lines in the drawing, I know this set is related to this set, and I know this set is related to this set. And so by the transitivity axiom, I can deduce for free, just from the existence of these two lines, that pair, set containing 1, set containing 1, 2, 3, that pair has to be an element of the partial order as well, even though I didn't explicitly draw out that line. And similarly, by the reflexivity axiom, I need to have the pair set containing 1, set containing 1. That has to be an element of R. But I don't need to draw a little loop from one to itself. That would be a perfectly valid thing to do. This would be a nicely described picture of a partial order. It wouldn't change anything. It would still be correct, but there's no need for me to include that line because the axiom of a partial order forces that relationship to be there. It forces that this set is paired with itself as an element of R. So this idea of drawing partial orders this way is to try to communicate the entire data of the partial order as simply as possible. Because we see up here, if we wanted to communicate partial orders in a precise way, one thing we have is we can sometimes write them concisely like this, but sometimes there isn't a really concise way to do this. Maybe we're not trying to order some things that we naturally view as sets or something, or maybe this like ordering by subset containment isn't quite what we want. So we could imagine just having some crazy collection of mathematical objects, and we don't really know how to order them, but I know I want this thing to be the biggest one, and I want this thing to be the smallest one, and then all this other stuff should be in between it somehow. And so you can try to like visually arrange this stuff into a picture until it becomes kind of a picture of a partial order. And so that's the idea of these pictures. They're supposed to describe partial orders without having to write down like an entire monster set of ordered pairs. And so that's the idea, is that we're just trying to describe the data necessary to construct that monster set of ordered pairs without actually having to write down all of those ordered pairs themselves. Okay. As a side note, something you might see in practice, people might put directions to these arrows if they don't want to use the vertical separation to imply the direction. So this would also be a valid thing to see, some arrows like this. Okay. So that's a nice example of a partially ordered set, and this is like a drawing of a poset. So let me title that. That's a drawing of the poset x, r that we described above. That's what we have here. Okay. So these drawings are useful because, like I said, they allow us to write down, or they allow us to describe all the data necessary to construct a poset without having to write down a crazy set of ordered pairs that would take a long time to do. So now let's try to think about some interesting, or like maybe let's try to just observe some things about this poset we were talking about, this x comma r. Something you might notice about this poset is that it's not like these things are all comparable. So the objects in this set X were these 5 sets: set containing 1, set containing 2, set containing 1, 2, set containing 1, 2, 3, etc. And we had this way to order them by subset containment. But interestingly, it was not the case that this was a subset of this, nor is it the case that this is a subset of this. So like the 2 singleton sets, set containing 1 and set containing 2, are what is called non-comparable. Neither one is related to the other by R. So that's an interesting thing that happened in this example of a poset that wouldn't have happened in our previous example of a poset. The other one we saw was just orderings on numbers, like our standard orderings on the naturals. And in that scenario, so for the standard partial order on the naturals, or the integers, or whatever, those standard partial orderings of numbers, right, naturals or integers or rationals or real numbers or algebraic numbers or any kind of algebraic real numbers, I guess, so, any kind of set of numbers that we naturally order, for those, we have the property that for all a and b, either a is less than or equal to b, or b is less than or equal to a. One of those two things is true for any 2 numbers I pick, right? Take any 2 real numbers, 3 and negative 7.2. One of those has to be bigger than the other. In this case, 3 was the bigger one of the 2 numbers I said. But that's just the case for any 2 numbers you pick, any 2 real numbers. So this is some property that a partial order could have, but not every partial order does have. Here, this partial order R didn't have that property. We did have non-comparable elements. So let me make that precise. Definition. Let's let x comma r be a poset. Two elements, let's say a and b in X, are called comparable, and this is with respect to the partial order R, if one of them is related to the other. So if A are B or B are A. Okay. So if one of those two statements is true, if A is related to B or B is related to A, then we'll say that the elements are comparable. And that's the case, for example, for any 2 elements of the real numbers. So, e.g., every pair of real numbers is comparable with respect to the standard partial order. Oop, didn't want that in red. So that's an interesting property that these standard examples of our partial orderings had that this more general example of partial ordering didn't share. This was a partial ordering that was also pretty natural. It came from just subset containment, which is a pretty big class of examples. But it has these non-comparable elements. These 2 elements were non-comparable, and also these 2 elements were non-comparable. So but on the other hand, these 2 elements are comparable, because even though I didn't draw an edge in this picture, this is less than or equal to this one according to the partial ordering of subset containment. Okay. So some partial orderings have non-comparable elements and some don't, and that's going to be an important concept for us. So I'm going to make another definition. Let me say a partial order on a set X, let me say a partial order R, on a set X is called total, so that's an adjective, or you could use the noun form, so you could say it's a total order if every pair of elements of X is comparable with respect to R. So let me just spell out precisely what that means. This means for all A comma B in X, A R B or B R A. So this is what it means for a partial order to be a total order, or you might say that the partial order is total, and it just means that every pair of elements is comparable. So this previous example I drew up here, this is not a total order, because there are non-comparable elements. It's not the case that every pair of elements of X was comparable in this case. Okay, so this notion of total order is very important, and just to repeat basically the note above, the standard partial orders on the naturals, the integers, the rationals, the real numbers are all total. Those are total orders, because any two numbers are comparable. One is going to be bigger than or equal to the other. And so in general, these partial orders don't need to be total. They can have non-comparable elements, and those are really important for us to consider. We really will care. We'll see many examples of why we care about partial orders that are not total. Those will show up quite a lot in math. But the total ones are also important, mostly because they have some nice properties. And we'll get to those properties pretty soon. Yeah. For now, I guess I just want to say that this concept is important, and there is this important distinction between partial orders in general and this special subcase of total orders, which are more well-behaved, but both are important. Okay, and so as a teaser for the next video, let me talk about some other interesting feature of this poset that we generated earlier. Actually, before I do that, let me just make another definition. Another definition is a toset, which stands for totally ordered set, is an ordered pair X comma R, where X is any set and R is a total order on X. Okay, so that's a toset. And as a teaser for the next video, let's look at an interesting property of this poset we produced earlier. This poset has two what are called minimal elements. These two elements are called minimal because there's nothing that's smaller than them in this poset. And these two elements are called maximal because there's something that's bigger than them in this poset. And so the interesting thing for us to notice here is that a poset can have multiple minimal elements and multiple maximal elements. There's no requirement that if something is as big as possible, then it must be bigger than everything else, right? So we'll see the distinction, or we'll try to understand when is it the case that these maximal elements will actually be bigger than everything else. Like this element here, 1, 2, 3, is maximal, but it's not bigger than every other element in the set because, for example, it's not even comparable to this other maximal element. So we'll try to investigate what's going on there and the importance of that concept in the next video.